You think you've got gravity figured out? Step on a bathroom scale. That number staring back, that's your weight, right? Earth tugging you down. Simple. Drop your phone. It smacks the floor. Moon loops around Earth. Planets trace lazy circles around the sun. Newton wrote the recipe centuries ago. Every mass pulls on every other mass. Easy, obvious. But what if I told you that picture isn't just a little incomplete? It's completely, profoundly wrong about what's actually happening. Because gravity, as you've been taught, isn't a force at all. And once you see what it really is, once the illusion shatters, the entire universe will look different. Let me walk you through it. Stand up. Right now, feel the pressure on the soles of your feet. That heaviness. What do you think you're sensing? Most people say gravity pulling me down. But think about the actual sensation. The floor is pushing up against you. That's the only pressure you ever feel, an upward push. You never feel the pull, only the push. Where is this mysterious downward force? You've never once felt it directly. So why do we still call gravity a pull? Here's something even stranger. The moon is falling toward Earth right this second. It's been falling for 4 billion years, yet it never gets closer. It just circles, forever falling, never arriving. What kind of pull works like that? A pull that pulls constantly but never pulls anything in? According to Newton's original idea, that pull happens instantly. Wiggle Earth and the moon feels it immediately across 250,000 miles of empty vacuum. Instantly. How? What carries the signal? What's the invisible messenger? Newton himself had no clue. He called it action at a distance and admitted it made no sense. But his math was gorgeous. His predictions were flawless. So everyone stopped asking the uncomfortable questions. They shouldn't have. Let's go back a few centuries. Nobody understood planetary motion. Copernicus said they orbit the sun. Fine. But how? What shape? Tycho Brahe built a castle observatory and spent decades recording planet positions night after night. Brass instruments, fractions of a degree. Why such obsessive precision? Because you don't learn nature's secrets by guessing. You look, you measure, you write down exactly what you see. That's where real science begins. Tycho's data landed in the hands of Johannes Kepler. Kepler wanted to find the true shape of orbits. He tried circles. They came close, but Mars was off by 8 arc minutes, 1/80th of a degree. Most people would shrug, measurement error, but Kepler knew Tycho's craftsmanship. That man did not make 8 arc-minute mistakes. So Kepler threw out his circles and started over. Years later, he found the answer: ellipses. Planets move in ellipses with the sun at one focus. Perfect match to the data. Elegant. But it raised an even bigger question. Why ellipses? Meanwhile, Galileo was doing something that looked childish, rolling balls down wooden ramps. Sounds trivial, but watch what happens. Roll a ball down an incline. It speeds up. Let it roll onto a flat table. It keeps going. It doesn't stop instantly. Now imagine you could remove all friction, no air, no roughness. What then? That ball would roll forever. Same speed, same direction, forever. That bothered people. Surely motion needs a continuous push. Surely things naturally come to rest. No, that's backwards. Motion is the default. Rest needs an explanation. An object moving in a straight line doesn't require a cause. That's the natural state. What needs explaining is change. Slowing down, friction, speeding up, a push, changing direction, a sideways force. This is inertia, Newton's first law, and it creates a puzzle. Planets should move in straight lines. That's their natural state. But they don't. They curve. Their paths bend constantly toward the sun. Something must be deflecting them at every instant. What? Isaac Newton saw the answer. Planets want to go straight, inertia, but they curve. Something continuously changes their motion. He called it gravity, a universal attraction between any two masses. The force depends on mass and distance. More mass, stronger force, greater distance, weaker force, specifically dropping off with the square of the distance. With that one principle, everything clicked. Why ellipses? Because planets are falling toward the sun while simultaneously moving sideways. The combination yields elliptical paths. Kepler's laws emerged naturally from Newton's force law plus inertia. Why does the moon orbit Earth? Same principle. It's falling toward Earth, but moving sideways fast enough to keep missing. It falls around Earth instead of into it. Why does an apple fall? Earth attracts it. Same law, different scale. Newton did a brilliant calculation. He figured out how much the moon falls every second, how much its path deviates from a straight line. Then he calculated how far objects fall on Earth's surface. The numbers matched perfectly when accounting for distance. Revolutionary. The force pulling an apple is the same force holding the moon in orbit. Heaven and Earth, identical physics. With Newton's law, everything made sense. Ocean tides, moon pulls on Earth's water, Earth's equatorial bulge, spinning comets. They return on predictable schedules because they follow ellipses. Strange observations found explanations. Jupiter's moons sometimes appeared early, sometimes late. Turned out light takes time to travel. That led to the first measurement of light speed. Planets wobble slightly because they tug on each other, not just the sun. From wobbles in Uranus's orbit, astronomers predicted a new planet, Neptune, and found it exactly where predicted. For 2 centuries, Newton's gravity stood as one of science's greatest triumphs. It explained everything anyone could measure, except one tiny detail nobody could explain. Drop a hammer and a feather in a vacuum. They hit the ground at the same time, exactly together. The hammer has more mass, so Newton's law says gravity pulls it harder, much harder. But the hammer also has more inertia. It resists acceleration more. These 2 effects cancel perfectly, not approximately, perfectly. Every object falls at the same rate, regardless of mass. Why? Newton's theory requires 2 different properties of mass. Gravitational mass determines how strongly objects attract. Inertial mass determines how hard they are to accelerate. And these 2 are always perfectly proportional for every substance ever tested to incredible precision. But why should the attracting property and the resisting acceleration property be perfectly equal? Newton had no answer. Just a beautiful coincidence that made the math work. Or was it a coincidence? Einstein asked a different question. What if that perfect equality isn't a coincidence? What if it's telling us something fundamental about what gravity really is? Here's a thought experiment. You're in a closed room with no windows. You feel your normal weight pressing you to the floor. Are you on Earth? Or are you in a rocket ship in deep space, accelerating upward at 9.8 meters per second squared? Can you tell the difference? Drop a ball, it falls to the floor in both cases. Throw it sideways, curved path in both cases. Stand on a scale, same reading. There is no experiment that can distinguish them. This is the equivalence principle. If you truly cannot tell gravity from acceleration, maybe they are the same thing. Maybe what we call sitting still in a gravitational field is actually a form of acceleration. Here's Einstein's revolution. Objects in free fall, the falling apple, the orbiting moon, astronauts in the space station, none of them experience any force. They are moving naturally, following their natural paths. No pulls, no pushes, nothing acting on them. But the apple is clearly falling. Yes, but what if the apple isn't accelerating at all? What if it's following the straightest possible path and it's space itself that is curved? This is Einstein's profound insight. Gravity is not a force between objects. Gravity is the curvature of space and time. Massive objects don't pull on other objects. They warp the space around them. They bend it, curve it, distort the geometry. The apple isn't being pulled to the ground. It's following the straightest possible path through curved space-time. But near Earth, space-time is curved, so straight points toward Earth's center. You, standing on the ground, aren't being pulled down. You're trying to follow your natural path through curved space-time, a path toward Earth's center. But the ground is in your way. The ground pushes you upward, deflecting you from that natural trajectory. That's what you feel as weight, not gravity pulling down, but the ground pushing up. Einstein made a concrete prediction. If gravity is curved space-time, then light should be affected too. Light has no mass. In Newton's theory, gravity shouldn't bend light at all. But if gravity is curvature of space itself, then light following the straightest path through curved space should bend. During a solar eclipse in 1919, astronomers measured stars near the sun's edge. The stars appeared displaced. Their light had bent passing near the sun, exactly as Einstein predicted. This is gravitational lensing. We see it everywhere in the cosmos. Massive objects bend light from more distant objects behind them, creating distorted rings and arcs. Direct evidence that space itself curves in the presence of mass. Astronauts in orbit look weightless. Zero gravity, people say. Wrong. The gravitational field at the altitude of the space station, a couple hundred miles up, is almost as strong as here on Earth's surface. About 90% as strong. So why do astronauts float? Because they're falling. The capsule is falling. Everything is falling toward Earth constantly, but they're also moving sideways very fast, about 17,000 miles per hour. As they fall, Earth's curved surface falls away beneath them. They keep missing. They fall around Earth instead of into it. Everything falls together at exactly the same rate, so there's no sensation of falling, no weight, no up or down. It feels exactly like floating in empty space, far from any mass. Free fall feels like nothing because it is nothing. That's the equivalence principle in action. Think of Earth's surface. It's curved, but standing on it, it looks flat. Here's something remarkable. Why is Earth round in the first place? Because of gravity, but not as a pull. Space-time around Earth's mass is curved equally in all directions. Every piece of rock, every drop of water tries to follow the straightest path through that curved geometry. When everything follows those curves from all directions equally, you get a sphere. The only shape where every point on the surface is the same distance from the center. Earth is round because that's what happens when matter follows curved space-time. The shape emerges naturally from the geometry. An ant walking what it thinks is a straight line on a curved surface actually follows a curve. But from the ant's perspective, it's going perfectly straight. That's what's happening with everything near Earth. Except it's not just space that's curved. It's space and time together, space-time. Massive objects create curves in space-time, depressions, wells, distortions. The sun creates a deep well. Earth creates a smaller one. Even you create a tiny well too small to measure easily, but it's there. Objects moving near these wells naturally follow the curves, not because anything pulls them, but because they're following the straightest possible paths through curved geometry. The moon orbits Earth because it's following the natural geometry of curved space around Earth. That geometry makes the straightest path into a circle. An apple falls because it's following curved space-time near Earth's surface. In that curved geometry, straight ahead through time points toward Earth's center. When you throw a ball, it follows a parabola, not because gravity pulls it down, but because it's moving through curved space-time, and the straight line in that curved space looks like a curve to you. You're standing right now, you feel weight. In Newton's picture, gravity pulls down and the floor pushes up, two forces balanced. In Einstein's picture, only one force acts on you, the floor pushing up. But if there's only one force, you should be accelerating. And you are accelerating upward constantly. The natural path through space-time points toward Earth's center. That's the free fall trajectory. But the floor is in your way. It pushes you upward, deflecting you from that natural path. You're like someone standing in an accelerating rocket. The floor pushes. You feel weight not from any downward pulling force, but from being accelerated away from your natural path. The apple hanging on a tree is also being pushed upward by the branch. When the branch breaks, the pushing stops. The apple is suddenly free to follow its natural path through curved space-time. It falls, but the apple isn't accelerating. The apple is finally free to move naturally. You standing on the ground are being constantly accelerated upward by the floor pressing against your feet. Falling is the natural state. Standing still requires a force. That's Einstein's revolution. Once you understand gravity as geometry, extreme phenomena make sense. A star is a massive ball of gas. Its mass creates a deep well in space-time. The natural paths in that curved space point inward. What prevents collapse? Pressure from nuclear reactions in the core pushing outward. Balance. When the nuclear fuel runs out, the pressure drops. Balance breaks. The star collapses. If the star is massive enough, the collapse continues until matter is compressed to incredible density. Atomic nuclei emerge. Electrons are crushed. What emerges is a neutron star, nuclear matter compressed to the size of a city. A teaspoon would weigh 1 billion tons. For even more massive stars, not even neutron pressure can stop the collapse. Space-time curves so sharply that all possible paths lead inward. Even light cannot escape. This is a black hole. Near a black hole, space-time is so severely warped that light itself, following the straightest possible paths through this geometry, spirals inward and never comes out. We can't see black holes directly, but we see their effects. Matter falling toward a black hole speeds up, heats up, radiates enormous energy before disappearing. All from one idea: mass curves space-time, objects follow the curves. From this one principle, everything follows. Planetary orbits, tides, the precession of Mercury's orbit, a tiny effect Newton's theory couldn't explain, but Einstein's predicts perfectly. Gravitational lensing, black holes, gravitational waves rippling through space when massive objects collide. The same principle explaining how the moon orbits also explains the largest structures we observe. Galaxies, clusters of galaxies, universal, elegant. Newton's equations work beautifully for practical purposes. We use them to launch satellites, calculate orbits, predict eclipses. They're simpler than Einstein's equations and accurate enough for most applications. But Einstein revealed what gravity actually is, not a mysterious force pulling objects together across empty space, but the curvature of space and time themselves. Mass tells space how to curve. Curved space tells objects how to move. When you step on that scale, you're not measuring a downward pull. You're measuring how hard the scale must push to prevent you from following your natural path through curved space-time. When you watch something fall, you're seeing an object finally free to follow the geometry that mass has woven into the fabric of reality. When you look at the moon, you're seeing an object following the straightest possible path through the curved space around Earth, a path that looks like a circle because space itself is curved. Space-time brings objects together. That's what we call gravity, not a force. Geometry, and that is far more beautiful than any mysterious pull could ever be.